Hi, this is a demo of how to read the new Tissues bar graph feature on the Shearwater Petrel Technical Dive computer. This demo will visually explain some of the Haldane decompression model theory without a lot of math. So normally the main screen will show this, and you can page over a few screens to see the decompression tissues bar graph. I've recompiled the firmware to show the tissues on the main screen. Now this horizontal axis is pressure. Now each one of these bars represents one of the 16 tissue compartment tissue tensions in the Bowman ZHL 16C deco model. The fastest tissues are on the top and the slowest are on the bottom. So what are tissue tensions? They're not gas in the gaseous state that's actually exerting pressure. They're an amount of dissolved gas that's in solution in the liquid tissue compartments of our bodies. So why do we call them pressures? Well, the reason we talk about them in pressure is because of Henry's law, which says that when you've got a gas-liquid interface, the amount of gas that can be dissolved in the liquid is directly proportional to the partial pressure of the gas in equilibrium with that liquid. So the important thing here is directly proportional to the partial pressure. And now this is great because for deco modeling, what we're interested in is whether the tissue is undersaturated and is going to be on-gassing, or it's supersaturated and will be off-gassing. So this graph can tell us that info. So how do we read this? The boundary of green and yellow here, that's ambient pressure. Currently I'm at sea level, so it's 1 absolute atmosphere. This vertical black line, that is the inspired inert gas parcel pressure. And now I'm at the surface, I'm breathing air, which is 79% nitrogen, so this line is about 79% of ambient pressure. This red-yellow boundary line here, that's the Bowman M value line. And now that's the maximum supersaturation allowed by the Bowman's original algorithm. We don't use it directly. We modify it by what we call gradient factors, and I'll demonstrate that shortly. Watch as I increase depth what happens. You'll see depth is increasing here. I've got this wired into a little pressure chamber so that I can simulate depth. It's transitioned into dive mode now, and you'll see what it looks like has happened is that the tissue loading has fallen, but it's not. The amount of gas that's dissolved in the tissue compartments hasn't really changed from doing that. It's been a very short amount of time. What has changed is ambient pressure. Ambient pressure is now higher. Now we're undersaturated. We're less tissue loading than the inspired inert gas pressure, so these tissues are on-gassing. As I go deeper, that difference will rapidly increase. Okay? Now what if I change to a different gas, such as 50% oxygen, a nitrox mix? Now the inspired inert gas pressure has just jumped to 50%. So for open circuit, it's very simple. The inspired inert gas pressure is just the fraction of inert gas times the ambient pressure. I'm going to switch back to my air because I'm too deep to be breathing this mixture. Okay, that's better. And I'm going to continue going deeper. And I'll stop at about 140-ish feet, and I'll just let you watch the on-gassing. I'm going to speed the video up now. During this time, watch how the tissue tension bar graphs approach the inert gas inspired pressure line. You'll see the fastest tissue approach the quickest, and you might also note that the rate at which the bars approach the inert gas inspired line is related to how far they are from the line. As they get closer, the rate at which they change slows down. You'll notice the fastest tissue is now almost saturated. It will not increase above the vertical black line. It won't go higher than the inspired pressure. Okay, now we're ready to head up. Until now I've talked about tracking the inert gas tissue tensions. The other part of a deco model is applying limits to the allowed supersaturations during ascent. Now actually the Bowman and VPMB models, they both track the tissue tensions in the exact same way. Where they differ is in how they determine the allowed supersaturation limits. So let's take a quick step back. When these tissue tensions get above ambient pressure, they're not going to get at above ambient pressure staying at constant depth. They're going to saturate at the inspired inert gas pressure. But as I decrease depth relative to ambient pressure, the tissue tensions are going to increase. We're going to get a supersaturation. When they increase to some value above ambient pressure, we're now at risk of bubble formation. The Bowman model sets fixed limits, which are described by linear equations, to the supersaturations. VPMB attempts to model bubble growth and limit the total number of bubbles and their total volume, and that's how it determines the supersaturation limits. This line here, that is the Bowman M value, or the maximum supersaturation pressure. I don't want to misrepresent this as being a fixed value. They vary with the depth, and the M values also vary between the different tissue compartments. But I've just scaled them all on the same scale so that we can more easily visualize them in terms of decompression risk. So this point here would be the 100% gradient factor. Ambient pressure, that would be the 0% point. So we have two conservatism values with the gradient factor model, and we can see what they're set to here. They're set to 30% and 70% right now. So the low factor, the 30%, that's at the deepest stop. It's going to say that the tissue supersaturation is allowed to get to 30% of the Bowman's original M value. At the surface, we're going to be allowed to go up to 70%, or the GF high value. At depths in between, we're going to linearly interpolate between the two. Now I'm going to ascend and speed up the video a bit. Okay, I'm going to stop here for a second. I haven't reached my decompression stop yet, but I want to point out a few things. First, you'll notice that the tissue loading has increased. The amount of dissolved gas in the tissues hasn't really changed. It's been a very short amount of time. What has changed is ambient pressure is now lower, so now we're into a supersaturation. We have higher than the inspired inert gas pressure. We also have higher than ambient pressure in some of the tissue compartments. We're starting to get into the zone where bubble growth can occur. But why I really stopped is I want to show you this. Because I have a better gas for this depth set, the main display would be showing you this. The gas in yellow highlighted. Tells me to do is go to select gas, and now I'm going to select this 50% deco mix, and I'm going to continue my ascent. Okay, I've arrived at my first decompression stop, and what you'll notice is that the leading tissue compartment is about 30% of the way between ambient pressure and the M value line. That is because my GF low setting is 30%, and we can see what it actually is, the GF99 value. Okay, it's telling us it's 27% right now. If we were to ascend to the 40-foot stop, it would have increased above 30%. That's why we had to stop here. So we're going to just, oh, it's cleared. I'm going to ascend up to that, and I'm going to speed this up a little bit so you don't have to watch the entire decompression. Note that the tissue tensions decrease while we're stopped at a stop. As we ascend to the next stop, which will happen now, the tissue tensions rapidly rise and then begin to fall again. Okay, I've reached the 20-foot stop, so I'm getting kind of bored. I'm going to speed up the decompression. You wouldn't be able to do this on an actual dive because, of course, you've pre-planned your gases. Right now I've got 6 minutes left on my 20-foot stop and a total time to surface of 22 minutes. Remember those numbers. What I'm going to do is I'm going to go into dive setup, define gas, and I'm going to define oxygen, 99% O2, close enough to oxygen for all intents and purposes. Okay, that's all I have to do to define the gas. I'm also going to have to go and switch to it. I'll do that quickly here. Okay, so currently my gas is 50% oxygen. Select gas. I'm going to select the 99%. Okay, I've changed the gas, and now the 20-foot stop has dropped to 4 minutes, and my total time to surface dropped from 22 minutes to 13 minutes. So why has that happened? Well, you see that the inspired inert gas pressure dropped from 50% of ambient pressure down to nothing. And the rate at which the tissue tensions are going to off-gas is proportional to the difference between the inspired inert gas pressure and the current tissue tension. So by having a larger gradient there, they're now off-gassing faster. We don't have any nitrogen, any inert gas at all in the breathing gas. Oh, a quick note is that with oxygen, you don't get any decompression advantage by going to the 10-foot stop. With other gas mixtures which have inert gas in them, you do, because you're breathing inert gas at a lower pressure when you're at 10 feet relative to 20 feet. With oxygen, you're not breathing any inert gas at all, so it doesn't make a difference if you're at 20 feet or 10 feet in terms of the rate of off-gassing. You're actually better at 20 feet from a decompression illness risk point because your tissue tensions relative to ambient are not as supersaturated. But breathing oxygen at 20 feet, you are pushing the partial pressure of oxygen up to the 1.6 range, which means you're at risk of oxygen toxicity problems with long exposures. Now I'm going to speed up the video. Okay, so the decompression has cleared. I'm going to ascend to the surface now, and we'll see that the tissue tensions will increase rapidly with respect to ambient pressure. Also, when we're on the surface, the dive computer always assumes that you're breathing air, which is why the inert gas inspired pressure has gone back up to 79%, even though we're set to oxygen. In a minute, it would transition automatically out of dive mode. I'm going to manually end the dive. We're back in surface mode, and I want to quickly show you that the GF99 value was just under 70%, and that is because our GF high conservatism value is 70. So that's what that means, and we can see it here in the tissue graph. It's about 70% of the way between ambient pressure and the Bullman's original M value line. So I hope that demonstration explains some things. As a disclaimer, don't use this in place of training. Anything you've learned here, I tried to keep it accurate. I may have made some tongue slips somewhere in there. If you watched the whole thing, congratulations. I'm sorry it's so long, but I wanted to get some good information in there. And I'm just going to fast forward it again a little bit, and you can watch the off-gassing on the surface. Well, that's everything. If you have any questions, please leave them in the comments area and I'll try to answer them. Also, if you've noticed any errors, please let me know and hopefully I can get around to fixing those. Thank you for watching.